All right, just a brief review of some of the limiting cases for our time dilation and length contraction equations. We look at the limit as the velocity approaches the speed of light, the time that we see elapsing while an object that's moving at the speed of light is moving past is infinity. And so essentially then, for any finite amount of time that elapses on the rocket's clock, if this were a rocket that could travel at the speed of light, infinite amount of time would pass on the stationary clock. But since an infinite amount of time is never going to elapse on the stationary clock, essentially another way of saying this is that time stops. You see the person, although ironically the person is moving at the speed of light, so it's the fastest speed that he or she can go. You see the motion that's taking place within the spaceship as having ceased. You see no time elapsing on the rocket's clock, and so time is just, it's come to a standstill. Okay, and so that's what you would see if you could watch an object traveling at the speed of light. So the question is then, can this ever happen? Well, no, not for a massive object, because you'd be dividing by zero in this equation, and the implicit assumption is that the time that elapses must be a real number, and infinity is not a number. Okay, and so that can't happen for regular massive objects. However, a photon, which we'll be talking about soon in chapter 38, always travels at the speed of light, has no rest mass, but essentially it's called a zero-time particle because its time is frozen relative to the rest of the universe. And so on the photon's clock, the photon could travel through the entire universe without any time elapsing on its clock. Okay, now how is this possible? Well, we can get that from the length contraction equation. We see here in the length contraction equation, limit as the velocity goes to c, the contracted length goes to 0. So if we were to look, for example, at a meter stick that's moving at the speed of light, and here I am holding the meter stick and then moving closer and closer to the speed of light, then I'm going to be length contracted to 0, so I become two-dimensional. The meter stick goes to 0, and in the direction of motion, I would have no length whatsoever relative to you watching me traveling at the speed of light. But I would see the whole classroom length contracted to 0. And all of the oval heads in the class would be two-dimensional, and we'll all be squeezed down into essentially the third dimension, the dimension of the width and the direction of motion, would not be there. Of course, again, this is not possible because the velocity can't be c in the first equation. It means that it can't be c in the second equation, even though it doesn't create any mathematical difficulties with the length being equal to 0. However, if we were to look at a photon, and a photon is always traveling at the speed of light, has no rest mass, so there's nothing to stop it from going that fast. As a matter of fact, you can't do anything about it. If it doesn't have mass, it just automatically goes the speed of light. And that we also showed from looking at the wave-like properties of the photon. But we'll be looking at the particle-like properties of the photon as a particle rather than a wave in chapter 38. Okay, so what does this mean then for the photon? Well, the photon doesn't see itself as moving, but the rest of the universe is passing by the photon at the speed of light. Okay, and so what that means is that the whole universe is length contracted to 0. And so that means the photon has nowhere to go. It travels through the entire universe. From its own point of view, it hasn't traveled any distance at all, and it hasn't taken any time because time has stopped for the photon relative to the universe that's watching it. And so it's sometimes called a zero-time particle for that reason. The photon can traverse the entire universe. That's the reason why photons can exist, basically, as infinite range particles, is that from our point of view, infinity is different than it is for a photon. Photon doesn't see that any time has elapsed. It's traveled the whole length of the universe in zero time because the length is zero. Okay, and so we'll talk more about that. But those are some limiting cases of this that work for zero mass particles. Now, we might wonder then, what other effects does holding the speed of light constant have on the material properties of matter? And so it turns out there's also an effect on mass and energy. And so the way to see that is, let's imagine that you've got two rocket ships that are moving very fast in opposite directions. Like this. Say this one's moving at 0.8 c in that direction. This one's moving at 0.8 c in the opposite direction. And they each throw a ball straight away from the ship in such a manner that if we were to look at it from the point of view of someone that's stationary relative to these rockets, that the ball would move along this kind of a path and then come back to the rocket. So while that's happening, the rocket has shot the ball up, but it's also moving in this direction. So this would be the diagonal path of the ball. Similarly for this ball. So these two balls are ejected. They're equal mass balls and are fired with equal velocities, so that the ball would be received again by the ship over here. For an elastic collision, it would be traveling the same speed that it was previously. So this is what we see then from a stationary frame. Both masses are equal, both masses are fired with equal velocities. But now if we go down into the B frame, let's call this A frame and B frame. From the B frame, this rocket isn't moving. And this rocket is moving very fast, but not quite the speed of light in the opposite direction. Okay, so the velocities don't add to something that would be greater than the speed of light because of the variations in length and time. But because this object sees this object's time as being slowed down, basically what's happened here is that as the rocket releases the ball, because time is going more slowly, the ball isn't projected as quickly. Okay? Because there isn't as much time to accelerate the ball from this point of view, looking up. And so this is how we would view the collision then. It would come up and then back down like this, because this ball would be moving faster, and so it would intercept this ball at a higher point relative to the B frame. And so the B frame then is going to receive the ball, but the ball will move past the midpoint, will hit this ball, which is moving more slowly. This ball has to be moving faster, and then this ball would bounce back up to the ship. Okay, and so that has to be the case, because from this point of view, the B frame looking at this point of view, we see that every motion is slowed down. So if you're throwing the ball, that whole process of throwing the ball will take will basically be in slow motion. It will take longer from this frame of reference, but viewing this frame of reference, see them throwing the ball in slow motion, so that means the ball's not going as fast. But if the ball's not going as fast, and it bounces back up, and these were equal mass balls, then what that means is that the ball must have acquired mass, because this ball must now be more massive. To make up for the difference in momentum, so that it can bounce this ball back down, this ball can come back up. There was zero net momentum in the system to begin with, right, in the vertical direction. Then we throw this object up and this object down. There's zero net momentum. And so that means that it has to be the same afterward as well. But momentum is mass times velocity. So if the velocity is lower, the mass must be greater than it is down here. And so here, this is a smaller mass, the original mass, but a bigger velocity. Okay? And so that means that there's an effect on mass, as well as on length and time. And so that relationship is we have to jump into center of mass frames and do a few manipulations. This is done in your textbook. But the result is that the mass is equal to the rest mass divided by the square root of 1 minus v squared over c squared. So this is the relativistic mass increase. Okay, so not only are the time intervals expanded, the length is contracted, but because the time intervals are slowed down, that makes the velocity less in this kind of a symmetric situation, but by conservation momentum, that means that the mass must be greater. And when we work this out carefully, we see that it in fact has the same square root factor involved in the mass increase. Okay? And so if we look up at the data projector, we can see this then for an object that's traveling, say, at 0, then its mass is going to be the same as its rest mass. If it's at 25% the speed of light, then the mass is going to have increased only by 3%. Okay? At 50% the speed of light, the mass increase is at 15%. At 75% the speed of light, it's at about 1.5 times the mass. So the mass is getting greater. At 80% the speed of light, 1.67. We go to 99.5% of the speed of light. And the object has 22.4 times more mass than it did in the rest frame. Okay, and so let's then calculate the mass increase if the velocity is 3/4 the speed of light. And so we could plug into this expression then. This would give us m is equal to m naught divided by the square root of 1 minus, and this would be 3/4 or 0.75 squared c squared over c squared. And so that would be m naught divided by square root of 1 minus 9/16. Then the c squared over c squared would cancel. And so this would be 16/16 minus 9/16. So that would be m naught divided by the square root of 7/16. Okay, so let's see if we can knock that number out real quick, and you might even be able to beat me to this. Since I have to go retrieve my calculator. Okay, so that gives us 1.51. Okay, so if we look back up here at the table, we see that in fact that is the value that's shown here for the mass increase at 75% the speed of light. And so that's how all of these numbers were obtained in this table. If we wanted to plot this up, we have kind of an interesting plot of mass versus velocity. It starts out at m naught. Okay, because when the velocity is 0, m equals m naught. And then it moves along fairly horizontally and then doesn't really get rolling until higher values for the velocity that approach the speed of light. And at that point, the mass goes to infinity. So here, that's v equals c, and then this is a vertical asymptote. And so this means that m approaches infinity as v approaches c, because the denominator of this expression will approach 0 as v approaches c. And we see then that we get more and more of an increase of the mass as the velocity gets closer and closer to c. So we might wonder then, well, why don't we see this kind of a situation in our everyday experience? Well, let's try here a velocity of 0.1 c. Okay, and so if we plug that into this expression, we'll get m equals m naught divided by square root of 1 minus 0.1 squared, c squared over c squared. And so that'll be m naught divided by square root of 1 minus, well, 1/10 squared is 1/100th, or 0.01. Okay, so we got a 0.01 here, but 1 minus 0.01 is 0.99. So that gives us m naught divided by root of 0.99. Square root of 0.99 is 0.995. So this is m naught divided by 0.995. Okay, so that's basically 99.5% of the value in the denominator. And so that gives us, when I take the reciprocal of that, 1.005 m naught. Okay, so if this were 1.01 m naught, that would be a 1% increase. And so what we're seeing here then is a 0.5% increase in mass at v equals 0.1 c. Okay, so that's not very much. But what's 0.1 c? 0.1 c is 3 times 10 to the 7 meters per second, or that's equal to 0.1 times 186,282 miles per second. That's 18,628 miles a second. So that's 1/10 the speed of light, is 18,000 miles a second. So you could go all the way around the Earth, 25,000 miles, in about 1.3 seconds at that speed. And that's only giving us a 1/2 of 1% increase in the mass. And so this is clearly only going to start becoming significant at speeds that are greater than 0.1 c. And so sometimes, somewhat arbitrarily, we'll define 0.1 c as our cutoff point. Where relativity becomes important. Okay, and so you could say, well, okay, what is it at regular freeway speeds? Okay, well, then it's going to be even smaller. You're going to be out to something like the 13th decimal place or so. And so I'm going to set up some kind of an exercise for you to try to work that out. But good luck trying to do it on your calculator, because your calculator doesn't go out 13 decimal places. So you'll have to use binomial expansion to get it. There are ways of doing it, and there are very accurate ways of doing it that you can't always count on your calculator to give you values like that, because we're looking at maybe 10 to the minus 12 or 1/trillionth of a percent difference, which is not really all that measurable. Okay, so if we look at this then, we see that just conceptually, if you start accelerating a mass, usually we think in terms of the force as equaling mass times acceleration, but the mass stays constant. Okay, here the mass increases. And so down here at 0.1 c, then you push on it, and basically all of the force goes into changing its speed. But because the mass starts to increase, at this point, you get to the law of diminishing returns, where the force doesn't go so much into changing the speed, but rather the energy goes into changing its mass. Okay, and so there's a different kind of an emphasis here. Here, this is regular physics where applied force causes a change in speed. According to the kinetic energy expression, which is our classical expression for kinetic energy, 1/2 mv squared. But 1/2 mv squared isn't valid up at this point anymore, because the applied force causes a change almost entirely in the mass, only a little tiny bit in the speed. Here, we have a little change in the mass, but not very much. So a little bit of it goes into changing the mass, but not much. Whereas here, almost all the force, which is in the form of work, increases the mass. And very little goes to changing the speed. So this is in our relativistic limit. As the velocity becomes close to the speed of light, then almost all of the energy goes into increasing the mass. Okay, but if that's the case, then perhaps there's a relationship between mass and energy that we're not taking into consideration when we look at a regular kind of a system that doesn't involve relativity. Okay, we used to think that we had conservation of energy, but that mass remained constant. Now we're seeing that essentially here, the energy is going into changing the mass when it gets to higher and higher speeds, and very little of it goes into changing the speed. So we kind of need a new relationship that connects mass and energy together. So where can we get that from? Well, first of all, we need to develop the idea of relativistic force. And by the way, our relativistic force had better connect back in to the Newton's law limit when V is less than 0.1 c. And so what we could do here to get relativistic force is think of that relativistic force as dp dt, where p is our momentum, which is mass times velocity. But we've already seen in that previous example that to maintain conservation of momentum, the mass has to increase. So this isn't our regular momentum equation, but is rather our relativistic momentum, where this is our relativistic mass times velocity. So that'll be m naught divided by the square root of 1 minus v squared over c squared times v. And then we're going to need to take the derivative of that to get the relativistic force. Okay, and so this is going to be then d by dt of m naught v divided by root 1 minus v squared over c squared. Okay, and so this means then that we need to write the velocity somehow as a function of time. So how can we do that? Well, we can do that here by using the chain rule. We can say that this is equal to dp dx times dx dt. I'm sorry, dp dv, sorry, pdv times dv dt. Okay, so the derivative of this expression with respect to velocity is then multiplied by the acceleration. Okay, so dp dv before was just mass. So this was just ma, right? Because p was just mv, and so dp dv was just m, so this is F equals ma for Newton's second law. But now we have a more complicated expression. Now we need to write the derivative of momentum with respect to velocity. Okay, so let's do that here. And if this is completely confusing you, go to the textbook and it also explains it. But hopefully this is going to make sense to you. All right, so let's write this then as m naught times d by dv of v times 1 minus v squared over c squared to the minus 1/2 power. Okay, and so then we can do this derivative, and that'll be, well, first times derivative of the second, so that'll be v times minus 1/2 times 1 minus v squared over c squared to the negative 3/2 power times, and then times the derivative of the inner function. Okay, so here that's going to be minus 2v over c squared. Okay, so that's first times derivative of the second plus second, which is 1 minus v squared over c squared to the minus 1/2 second times derivative of the first, which is just 1. Okay. And so let's, here this minus is going to cancel out with that minus. That 2 is going to cancel out with that 2. And so basically then what we have here is v squared over c squared divided by 1 minus v squared over c squared to the 3/2. Okay, so that's this term. So here's our v squared, the minuses cancel, the 2's cancel, so it's just v squared over c squared. Then over here, I'm going to rewrite this as 1 minus v squared over c squared times 1 minus v squared over c squared to the 1/2, like that. So I'm rewriting this as this, where this is in the denominator, but then this becomes 1 minus v squared over c squared to the 3/2 in the denominator, and in the numerator we get 1 minus v squared over c squared. So now, these are both under a common denominator, and by the way, the m naught should be maintained here. M naught times this whole thing. This is m naught c squared. This is m naught. All right. So this then becomes m naught. The v squared over c squareds are going to cancel. So then this is going to be divided by 1 minus v squared over c squared to the 3/2. Okay, so that's our dp dv part of this, times dv dt. Okay, so the force then is going to equal this all times dv dt. Right, so that's equal to m naught a divided by 1 minus v squared over c squared to the 3/2 power. So we see then that our relativistic force depends on 1 minus v squared over c squared, but now it's to the 3/2 power, and if v is equal to 0, then this just becomes F equals ma. So that's our expression then for our relativistic force. Our relativistic force is m naught divided by 1 minus v squared over c squared to the 3/2 power times the acceleration a.